Myself, Srihari Karnam. Uh, I have over 2 decades of experience in spanning over embedded systems, edge systems, or supercomputing systems. Right? So I'm working in Intel right now on one API solutions, library, compiler, and other APIs. With me co-speaker Judhajit Dutta. He is RNI lead in TCS. His areas of specialization HPC, AI, parallelization, optimization, and exascale computing systems. So this talk we are going to keep the presentation at very high level, maybe 30,000 feet high. We have prepared this presentation when we were flying from Hyderabad to Bangalore. Right? It's all 30,000 feet view, which we are going to show you. So, before diving into compiler space, I will just give you a little overview on what is AI. Right? So, recent trends on AI looks like extended or total Turing test. Turing test, you all know, right? It is now called as extended or total Turing test. Earlier, Turing test was mainly onto the conversational area, but now the Turing test is extended towards intelligent robotics or generative AI, automotive reasoning, etc. So the next one is deep learning and generative AI. We all know there is a lot of hype with respect to generative AI and deep learning, uh, mainly with the advent of ChatGPT kind of solutions. But if you look at the reality here, hype is there, but there are challenges around the data bias and the different computational needs, the cost incurred in the deep learning space or generative AI training space. There is all great philosophy here around weak and strong AI, human-centric and responsible AI. So the research trend is towards how closely we are moving towards matching the human intelligence. And the other impactful areas or the adjacent areas around AI is like computational neuroscience, brain-inspired science, quantum computing. A lot of speakers before us spoke about the graph theory, optimizations around inferencing or training space, compilers, first level of IR, second level of IR, all these areas. Right? So the question we need to ask is about: is AI solving all of our problems, or are there any different opinions? Um, Next, we'll see actually how AI algorithms and the compilers are getting connected here. There are different AI algorithms in different domains, which has different computational requirements spanning across general purpose CPUs, GPUs, and TPUs, pre-configurable architectures, domain-specific architectures. Each will have its own requirements. A few algorithms are very well suited for sequential execution, or few algorithms might need only CPUs, which are good with the matrix multiplication unit under the hood. Few applications might need embarrassingly parallel hardware architecture like GPUs and all. So right now we all see a trend around domain-specific accelerator, domain-specific languages, which are solving a lot of challenges with respect to that particular domain, not the application-specific ASIC kind of architectures, but it is solving the overall domain in that area. Now, Compiler is connecting these algorithms to the hardware, right? Uh, lot of speakers before us, they spoke about how compilers are connecting the application space into the hardware. Initially, the compiler will actually take the algorithm, generate its computational graph. Right? Computational graph is the first level of intermediate representation. Then eventually there will be a backend to it. There's a second level of intermediate representation. Finally, the code generation happens at the hardware. So this is how a typical AI algorithm application space connecting to the lower level hardware. And there are different compilers here. We all know the language compilers are like NVCC, HCC, and SQL compilers. And the deep learning compilers include TVM, Flow, XLA kind of compilers. A lot of speakers spoke about these. And the optimization space is divided into the front end portion, which is the device independent optimization, and the back end one is device dependent optimization. So the front end side, a lot of the computational graph you see, operator level or the operator fusion kind of optimizations happen at the front end, and eventually when you go till the CUDA kernel level, the kernel level optimizations happen at the back end. So the model view of the compiler, we, you will see the model view of compiler in the two aspects. So one is you see a lot of automatic techniques which are being applied at the front end and the back end or intermediate representation areas, and uh, how these compilers are solving the data locality and the parallelization problems. And there is a lot of research focus around DSL to DSA or DSL to general purpose accelerators in the industry. Uh, we also see the auto parallelization and auto tuning with respect to the compilers front end and the back end portion. So mainly yeah. So I have listed some of the research areas or the innovations happening around the compiler intermediate representation. Right? We will not be touching the high level application space for these optimization. Application space keeps intact, and the main optimizations will be applied at the intermediate level so that these optimizations are not visible to the user. Right? It's like the code or application is intact, but the intermediate representation is a space where you can do the auto tuning and auto parallelization. Uh, yeah. So this is a high level summary on how algorithm is getting connected to application compiler and how compiler is actually generating the code to the backend. Yeah, now Judhajit will explain actually about how this is impacting the HPC class AI and other industry areas.
Thank you, Srihari. Yeah. Hope I'm audible. Okay. So this talk is a little bit holistic view of the HPC class compiler, what is exactly happening. So Srihari discussed about kind of a very high level what exactly we think about a little bit of AI, and then we move into how AI is connected to the AI algorithm connected to the platform which running the AI and compiler is connects. So this is also one part of the game, and what are the challenges happening, and what are the technology tools and textbook type of information technical or technique available. Some innovations available over here. Now there is one more area is there, that is the HPC. Now HPC we define a kind of HPC we define specifically in a textbook level. It's a kind of high precision floating point number, especially IEEE is 754, and it is probably a double precision floating point, 64-bit floating point numbers. And those kind of simulations running on kind of exaflop or even exaflop or petaflop systems. We be able to reach the two systems all over the world, able to reach the exaflop system, for that is the AMD Frontier, another is the Intel Aurora. And other from last year it is Ignite for the exascale AI supercomputer also. And if you see exascale supercomputers, several companies like Tesla, even Meta and all others, they are trying to create the AI centers in on-premises and other. And even cloud also, this year, probably a few months ago, a few weeks ago, Oracle announced that they were to provide probably Judhajit supercomputer into the cloud itself. So what does this mean, and why do you need this kind of extraordinary computers, and what are the cases for that? So we find out there is main typical two cases here. We are going to use those kind of high computational speed. One is you might be we are in a bigger high, and one is the large language model itself. They are training, or large visual models. They are training. But they may not be follow the exascale definition or the supercomputing definition exactly. But we make it as a class of warehouse scale computing or warehouse scale computing. But these classes using the speed, even a different level of the precision depending on the way we optimize the systems. So this is one part of the game. And another part, it's a serious work on the exascale supercomputer, where exactly AI augmented the science, explorations from the material science to biofuel, biotechnology, computational biology. Most of the cases those NP-completeness algorithms, genomics, and high energy physics, cosmology. So several domains affected over there, and they are coming out with a lot of partial differentiation solvers with kind of different techniques. And those techniques is augmented by AI also. Even for these physics, multi-physics data and the science data are also more structured way that people are such a big data that people get the data to create the feature and other things. Most of the cases, sometimes it may not be precision, not going to be compromised over there while running those kind of applications. Even this is next level inference also. So this is the two class we define as we think about AI HPC class here. But while running those kind of HPC class, like around the simulations, we have several challenges over here. And probably compilers and things going to solve a lot of issues in this case. Now that is the reason if you see there is a race behind the exascale AI supercomputers, even for the different organizations who are running the tools like CERN, Department of Energy in USA, or several other government agencies who is running the working on the core sciences area. They are actively exploring in this space. Yeah. Now, direct benefit for this science exploration. Now, I'm going to go to the next page because of the time. It just take a little bit. Yeah. So, now. So these are the main challenges over there. Of course, energy and power efficiency. So there's a paper came out from the Nature that all the world electricity public by the data centers. How to stop that? So it is not only the compiler tasks, and so several types of device architecture, the ecosystem, the scheduling system, computing workflow system. Now efficiency and productivity of the performance, because domain scientists, those who are working on science, they may not be willing to use the complex high-level programming language. Sometimes they are going to useful for the domain abstraction. So DSL one of the solution for that. But then with the performance, so that the performance comes out from the domain-specific accelerator, even for the general purpose accelerators. And how to connect this? How to quickly enable this domain-specific language to the general purpose or domain-specific system, which is running into the kind of the directly distributed area. Third challenge is HPC class software entire ecosystem is completely imbalanced. Even 2022, Jack Downbetter provided Turing Award, and he himself is backed up that entire HPC ecosystem is right now out of balance, and we need to create more of it. The library to compiler to enter system change, there is a different way to work on it, and it's required kind of a huge level of cooperation all over the world for the different researcher companies and other. Third part, the compiler. This exascale system, when it is running, and perhaps it is one of the least publicized area into this area because of this subcase, and that is the reason compiler comes into the picture once and again, not only for the user. Last part. So little bit misnomer, but we are use AI for AI compiler. It's actually use AI for the HPC compiler itself. So what are the options we have? What is the things in our sleeve? So ILS tuning, probably next a lot of people discuss a lot of things over there. So optimal decision for the compiler constructions, predict AI model for the runtime, understand your things metrics over there. So this is as a whole, and the parallelization points to the thing is. And I'm sorry, we're a little bit shortage of the time right now. So and thanks a lot everybody. Yeah.
Thank you. Next time we'll come back with a detailed presentation. So it was all complete rush. We were rushing through. We had a lot of data. So next time, give us 45 minutes. We'll give demonstrations. We'll walk through the industry trends, challenges. Right now, I have to just brisk, right?
This thing is time for 5 minutes. So we have 5 minutes for questions. We have questions from Professor Krishna.
Hi, excellent talk.
Yes, sir.
I wanted to get your opinion on which problems cannot be solved in this compiler technology using AI. That's
Which problems?
Which problems you think that cannot be solved using compiler using AI in this case?
In this space, the problem mainly the solution is the this kind of system probably running on a few hours. Probably they created a simulation job, probably 72 hours, 100 hours, even more, even for weeks. So those simulations are typically for the using some kind of partial differential solvers within non-linear and linear.
No, I guess my point is you listed different problems in compiler technologies like parallelization, program analysis, synthesis. Which problems in compilers you think cannot be solved by AI? Not which problems in general cannot be solved in compilers.
Sir, that I cannot be much better. It is depends that is here for next last week. We will discuss about that. Yeah. So this is cannot be solved means of course this kind of argumentations is a lot of challenging. In my cases, I can tell while we are running the system in a distributed memory scale. So we have both the cases of the distributed memory. Sometimes we write shared memory and mix it. This compilation sometimes it's going to be very complicated. Second part, while mixing one more heuristic of the AI, it turns around. It's not working at all. Honestly, maybe some other people are there, maybe different opinion. What exactly we have seen. So that is one of the part people are everywhere working. But AI cannot solve all the area of the compiler. I think extraordinary experts are here. So we are here also listen to them also. Thank you, sir.
Any question?
Yeah. Yes, sir.
So you said you are working on the intermediate code, other than the user code. So, and you said you are trying for automating the whole thing. Are you considering some kind of a hash pragma kind of a thing in the intermediate code? Is it, see, because once you go for full automatic, it's always a challenge and a problem. So, have you considered using some kind of annotation in the intermediate code for optimization?
You will get it, right? Okay. So, sir, here problem is here that not always going to be we are going to be over there. It depends on the kind of mathematical algorithm we are going to solve. depending on how many primitives available and other things and the hardware to be targeted. That is still dependency over there. So if we say directly right now, it is still in a semi-automatic manner.
It is semi-automatic.
Yes.
Yeah, it's not fully automated. Sometimes actually we are leveraging, as the speaker mentioned, right? We were leveraging PyTorch inductor code, right? Whatever PyTorch inductor supports about the automation and all, so that portion only we were using under the hood, right? So most of the time, whatever it supports, we are leveraging that. So,